in order to find the principal stresses, we need an initial stress state. To find the initial stress state, we're going to need to make a cut through that element so that we can see what the loads are and therefore what the stresses are acting on our element. Right, so cutting it just for this, I'm cutting it through the middle, but it doesn't matter if I'm in the middle or somewhere to the other side of it. The loads inside are going to be the same. So on my right-hand side, I'm applying this external torque of 20 pound-feet. An axial load of 200 pounds. Internally, I'm going to have this internal normal force, regular P, outward from the normal, outward from the cut surface. And then I'm going to assume that around that direction, I'm going to have my internal torque T. Right, so that's positive around the vector P. I would also potentially have bending stress, things like that, but in this case, those are all going to go to zero. The shear forces will be zero. The bending stresses will be zero. I will only have a P and a T in this case, as well as I have to consider that internal pressure as another source of stress on my element, but I'll get to that in a minute. So in this picture, in the x direction, I'll have negative P plus 200. So my internal normal force is a positive 200 pounds. And summing moments around the x-axis, I'm going to have a positive 20 pound-feet. And then T is going to be negative around my x-axis, so minus T. So my internal torsion, positive 20 pound-feet. I have the two internal forces, P and T. I have a pressure that's also going to cause a stress. So I now need to start assembling my stress state for that point A. So I'll start here by looking at the internal pressure first and see what is the stress state that it causes. And for these pictures, I'm actually going to stick with, well, I'll start assembling it with my x, y, and z coordinate system. So that cube is going to be aligned the same way as that stress element. All right, so due to pressure, I'm going to have, on what faces will the pressure cause stresses, and what type of stresses will we have? So right, the longitudinal is always half as much as the hoop because this is a cylindrical pressure vessel here. And the hoop stress, we're going to use the pressure times the mean radius over T. So we had internal pressure 500 psi, so we're in pounds and inches. The mean radius is going to be the internal radius plus half of the thickness, or the average of the internal and external radii. That'll be 0.25, which is the internal radius, if our diameter internally is 0.5, plus 1/2 the thickness, 0.025 over 2. Over the thickness, 0.025. So for the hoop stress, we get 5250 psi. And we can either recalculate this, or we know that the longitudinal stress is half of the hoop stress. So I can jump to divide this by 2. So 2625 psi is the longitudinal stress due to that internal pressure. So on our element, again, aligned the same way as that initial picture, we have normal stress on the x faces and on the y faces due to the hoop stress, due to the longitudinal stress. We still have to consider what stress is due to P and T. Due to the internal loads, we go back to how we were doing it before with our combined loading. I want to look directly at that cut surface and what's happening. Again, it doesn't really matter where I put this element, but I'm putting it on the outside surface. I'm just going to put it on the left side here, but we're going to get the same, no matter where it is on the circumference, we'll get the same principal stresses, even though some of the directions would change. In this picture, Z is right, Y is up, X is going into the page. And again, acting on this, I have my torsion, which is going to be positive around the negative x-axis. So if x is into the board, it's positive around the negative x. So my torsion is 20 pound-feet. My value of P was positive, and my assumption was it was in the negative x direction. So I have this value, 200 pounds, coming out of the paper. I know my internal radius is 0.25 inches. And I know that my external radius, or my outside radius, is 0.275. So based on this information, I need to find what's the stress due to the axial, the internal normal force P, and the torsion T. So I know I'm going to need these values. Since it's hollow, the surface area of this cut surface is pi r outside squared minus r inside squared. So the cross-sectional area is going to be 0.0412 inches squared. And I need that for my P over A calculation. And the polar moment of inertia J, again, it's hollow, will be pi over 2 r outside to the fourth minus r inside to the fourth. So the polar moment of inertia is going to be 2.85 times 10 to the negative 3 inches to the fourth. Right, so now I'm ready to calculate the stress acting at this point A, which I chose to be on this left side here. Right, so there's going to be a normal stress due to the axial load, P over A. So we'll get 200 pounds over the cross-sectional area, which we just calculated. So the stress due to P over A, I get 4850 PSI. And we'll be careful, what face is this stress acting on? First of all, it's positive. It is tensile. What face does this act on, or what pair of faces does this act on? It's pulling out from this X face here, or really this is the negative X face, but it's going to act the same on the positive. We have a tensile stress on that negative X face of 4850 PSI. So putting it into this viewpoint, 4850 PSI due to that, again, that normal stress from P over A. And then I'm going to have a shear stress due to the internal torsion, T rho over J. At the point A, which is on the surface of this pipe, well, first the T is going to be equal to 20 pound-feet. But our J is in inches, and our rho is going to be measured in inches. So I need to multiply by 12 to get into pound inches. Rho is the distance from this point to the center, which is our outside radius, 0.275. And J, which I calculated earlier, 2.85 times 10 to the negative third. So the tau we get here, 23,200 PSI. We know its value. We now have to represent it. So on what face is this acting, and in what direction does it act? It's going to be pointing in the negative y direction on the negative x face. So this is, again, we have to be careful with the coordinate system here. I expose the negative x face here, comes down the negative y direction on the negative x face. So here, the negative x face is this one. It points in the negative y direction. Right, we have our separate stress cubes. I now want to draw my initial stress state due to these three stresses, the stress from torsion, the stress from the axial load, and the internal pressure. And it does turn out, if we are in plane stress here, I can represent it in 2 dimensions if I flatten it down. Right? So since nothing is acting on this Z face, either shear stresses or normal stresses, I can represent this in 2 dimensions like we've been doing. Now I just have to look what's happening on each of my faces here. On the Y face, I only have a normal stress due to the internal pressure. So on my Y face, I have a tensile 5250 psi. On the X faces, though, I have stress due to the internal pressure, which is tensile, and stress due to the axial load, also tensile. So in my complete stress state, I have to add these 2 effects together to get the total stress in the X direction, 7475 psi. And between the 2 pictures I made, I only have 1 shear stress, so I can just copy that exactly. What are my principal stresses, since that's the end point of why I need it here? First, I need to identify, again, with the correct sign from this picture. My sigma x is 7475. Sigma y is 5250. And tau xy is going to be a positive 23200. Everything in psi. I won't go through all the calculation steps, but sigma 1, sigma 2, I calculate the same way I did in the previous problems here. I really don't need sigma average and tau max in this case because I'm not asked for the maximum shear stress, but I need them anyway to calculate the principal stresses. I get values here for the principal stresses of 29,600 and negative 16,900 psi.